Okay. Hi. Today I will begin by discussing solutions of the written test problems. The written test was given to my students on Saturday, and not all the students were able to solve all the 5 problems of the test. So we will discuss the solution now of the first problem. The first problem was that. Problem number 1. A rock with a height of 100 meters stands in the ocean at the equator. At sunset, the shadow lay at the foot of the rock. Determine the time when the Earth's shadow will reach the top of the rock. The Earth radius is given. So we have the planet Earth with a given radius, and somewhere there is a sun, and the sun rays go something like this. They go at all possible directions, but what we are interested in is the only ray which goes close to the Earth's surface. And here is the rock of 100-meter height. And when the Earth rotates, if this is a North Pole here, then rotation takes place in this direction. When the Earth rotates, this rock will move somewhere in this position in some time. So this is the initial position of the rock, and this is its final position when the top of the rock will go into the shadow of the Earth. This is the Earth's shadow at the sunset. So when we are here at this point of the Earth, the sun is just above the horizon and the sun is setting down as the Earth is rotating. So we need to calculate the time which takes for the shadow to creep from the bottom of the rock to its top. The Earth radius is given. It's known to be about 6,400 meters. And so we have to find how long will it take for the shadow to cover all the rock. So we need to calculate the time which takes the Earth to rotate at this angle alpha. If we know angle alpha, then we know the time necessary for this motion. So the time which takes the rock to move from this point to this point is proportional to angle alpha. And we know that 24 hours, that is the period of Earth's rotation, takes just 2 pi angle. That is the whole revolution of the Earth. 2 pi angle equals 2 pi in 24 hours. From this proportion, we can easily find the time, which will be the period of Earth's rotation over 2 pi times angle alpha, which is certainly, period is about 24 hours, so it will be 12 over pi times alpha. And what we need to calculate is alpha. It's easy to do so because we know the height h of the rock. So if we know the height, then you were given a hint in this problem saying that sine alpha is approximately equal to alpha if the angle is very small. And we guess that the angle is very small because the Earth's radius is more than 6,000 kilometers. This is certainly kilometers. More than 6,000 kilometers. And the height of the rock is just 100 meters. So this is very small distance as compared to the radius of the Earth. If it's very small, then the angle alpha is also very small. So it's possible to use this approximation to calculate sine alpha and to calculate alpha. Alpha is practically the sine. The sine is is what? Is the opposite leg of this triangle. The opposite leg, let it be A, and this point is B. So AB times AC, for example. So alpha will be practically equal to the sign, which is AB, the opposite leg of this right triangle, to AC. Now, what is AB? Can we find it somehow? Certainly. We know the one leg of triangle, and we know this side because it's given as radius plus h. So we know AB from a Pythagorean theorem. AB will be equal to the length of this side squared, that is r plus h squared, minus the length of this leg squared minus r squared. And AC equals r plus h. That is Pythagorean theorem. Yes, everything's correct. So how can we tackle this expression? Under the root, under the square root, we have the difference between two squares. So the difference between two squares, we can just open this round brackets. The easiest way is to open this round brackets. It will give us r squared plus 2rh plus h squared minus r squared under the square root divided by r plus h. R squared cancels here, and what remains is h can be taken out of the round brackets. We say h can be factored, so h times 2r plus h. We factor h over r plus h. Now we take into account this fact that the Earth's radius is much, much larger than the height of this rock. The height of the rock is just 1/10 of a kilometer, 1/10, while the Earth's radius is more than 6,000 kilometers. So the Earth's radius thousands and thousands times larger than the height of the rock. So we may neglect the height of the rock here as compared to the Earth's radius. And also we may neglect it here. It's very small additive. It can be neglected without any problem, especially because you are given this condition, this hint for approximation. So what we get in as a result is the square root of 2rh divided by r. And what you need now is just to substitute the values for r and h and conclude this calculation. Or you may substitute this expression for alpha here and obtain the expression for the time interval as 12 over pi times alpha, and alpha is square root of 2rh over r. If you carry out these calculations, you will obtain something like approximately 1 minute 70 seconds, something like that. Depending on how you calculate, what method of calculation you apply in this problem. You may take 1 minute 20 seconds, it's not a mistake. 1 minute 15 seconds, it's not a mistake. But if you use calculator, you will obtain something like 1 minute 17 seconds and some other portions of a second, which are absolutely not important here. Portions of a second may be neglected. So such is the correct solution and correct answer to the first problem. Let's now discuss the second problem solution. That's the second problem is as follows. A bar of mass m is on an inclined plane with an angle alpha to the horizon and coefficient of friction k equals 1. So what we have here is an inclined surface or a slope, angle alpha, and the bar of mass m is here, and the coefficient of friction is given. And the question is, what horizontal force should be applied to the bar so that it does not move? What horizontal force? What is horizontal? Not every student was able to understand what is horizontal. Horizontal is parallel to this side. Horizontal force is applied in this direction, not along the slope as some students mistakenly thought. The force F, outside force, is directed not along the slope, but it's directed horizontally. So the force F is directed here. And what other forces, by the statement of the problem, and what other forces act on this bar of mass m? Certainly a force of interaction with the Earth, a force of gravity mg, and certainly a force of reaction, which is perpendicular to the surface, and certainly a force of friction. Well, where is that force of friction directed to? Suppose force F, external force, is 0. If there is no external force, then the bar will want to slide down the slope, and the force of friction will be directed this way in order to retard the velocity of the bar. So if the bar wants to slide down, then the force of friction is directed oppositely to the direction of motion. This will be the case if the force F is 0 or very small. And this also will be the case if the force F is negative. Negative force is also possible. What does it mean, negative force? It means that it will be directed here. It means that we have attached a thread to the body M, and we pull this thread in this direction. It's quite possible. This is also the force with horizontal, directed horizontally. So the problem does not specify what is the direction of this force. We can either press with our force against the slope in this direction, or we can pull by the thread in this direction. So if the force is directed here, let it be positive. If the force is directed here, it may be negative. It will be negative in this case. So the force may be 0 and maybe very small positive or maybe even negative. And if we don't consider large forces, then it's obvious that the force of friction will be directed here. For not very large forces or even for 0 forces, the friction will be directed here. Let's take this direction for granted, and we know that the force of friction generally is related to the force of normal reaction. And we know that the coefficient of friction doesn't always take its maximum value. The coefficient of friction is not always maximum. This is the maximum possible coefficient of friction. But if the body is just on the horizontal surface, what forces of friction act on this body in this situation? We have only the force of gravity and the force of reaction, of the surface, and no friction is here. No friction. So in this case, when the body is in horizontal surface, the force of friction will be 0. The force of friction may appear if we try to push this body sideways. Then the force of friction will be somewhat larger than 0. How large can be the force of friction? That is the largest possible the largest possible magnitude of the force of friction if we substitute here the largest possible coefficient of friction. But if there are no external forces, then no forces of friction, and then in this case the coefficient of friction may be considered as 0. This is a convenient mathematical way to tackle this problem. This is a convenient way to understand what happens here. If we assume that the coefficient of friction may be between 1 and -1, that is, the maximum values for this coefficient corresponding to the maximum possible magnitudes of the force, and the force of friction may be directed upwards if the body wants to slide down the slope. But if we press too hard with the force F, if the force F is very large, then this body may want to slide up the slope. Yes, we push the body and will slide up the slope. In this case, the force of friction will be directed oppositely to its displacement, in the opposite direction. This can be tackled easily if we assume that the coefficient of friction in this formula is negative. And negative maximum quantity is the same as positive. Coefficient of friction may not be larger than unit in this particular problem. So after this analysis, we can write down all the necessary equations to consider this problem. So both force of friction and the applied external force may change their directions. The force of friction may be directed either up the slope or down the slope, depending on what is the direction of motion or intended motion of this body. Also, the force F may be positive or negative. If we push the body in this direction, then the force of F is positive. But if we pull this thread attached to this body, then the force of friction will be negative. All this can easily be taken into account by our algebraic consideration. And what is the consideration here in this problem? We have to choose some axis. I would like to choose vertical and horizontal axis to find all the necessary components of the forces. And if we consider motion along horizontal direction, then we have to take into account only the forces which have horizontal components. mg has no horizontal component. The weight is directed vertically. It will not be present in this equation. What is in this equation? If axis directed to the right, then all the forces looking to the right will be positive, and all the forces looking to the left will be negative in this particular case. So if we take the axis in this way, we could have chosen other direction. It's not important. It's not crucial what direction you choose as positive. It's up to you. So if this angle is alpha, then we have to indicate where is alpha. Alpha will be here, and also alpha will be here, and also angle alpha will be here. So all these angles indicated are equal to alpha. And so we have along the x-axis positive force N sine alpha in positive direction of x-axis. In negative direction, we will have minus force of friction F cosine alpha minus external force F. All the forces must be equal to 0 in this horizontal direction. Now in vertical direction, upward is positive, so N sine alpha will be, this component of the force N will be directed upward, it's positive, and plus force of friction N sine, N cosine must be here. Certainly, N cosine is vertical direction, certainly. Cosine alpha, this one, this is vertical That is certainly cosine because this is adjacent leg in this triangle. And f times opposite leg, it means that f sine alpha. And in negative direction, the force mg equals 0. The force F is horizontal, so its component in vertical direction is 0. It's not here. It should not be taken into account in the second equation. So we have to take into account that F is Kn. We have to substitute here instead of F this expression. And then we will have the possibility to find N from the second equation. I will put it in this way: N cosine alpha plus force of friction is Kn sine alpha equals mg. From the second equation, we can immediately find N. That will be mg over cosine alpha plus k sine alpha. And this expression for N can be substituted into the first expression to find what we need to find, force F, external force F, such that all these expressions are equal to 0. The force F is applied in such a way that the body is not, does not move. The body remains in the state of static equilibrium. It's at rest. If the body is at rest, its acceleration is 0. So in the second Newton's law, here we have 0. And we have to find force F from this condition. So by substituting N into the first equation, we will find that force F equals, if we take force F into this side of equation, we will immediately find force, which is N. I would put it this way: N cosine alpha minus coefficient of friction. No, this is sine alpha. Coefficient of friction cosine alpha. And continuing this formula, by substituting N, we obtain mg sine alpha minus k cosine alpha over cosine alpha plus k sine alpha. That is the expression for F. That is the correct expression for F. And that formula needs a little bit of analysis. First, we need to make sure that the formula is correct. It's physically reasonable. Well, how can we make sure that the formula is correct? For example, if coefficient of friction K is 0, for example, no friction at all, then we substitute 0 here, and we get no second term in this formula, and we get just sine divided by cosine alpha. This is tangent alpha. And we obtain a very well-known formula for the force which is necessary to sustain this body at rest if the slope is frictionless. If the surface is without friction, then that will be mg tangent alpha. Tangent alpha, so this formula goes to mg tangent alpha if coefficient of friction k is 0. If k is 0, then we obtain tangent alpha. This formula is very good for analysis. For example, if alpha is 0, then the force will be 0. What does it mean, 0 alpha? It means that the body is on a horizontal surface with 0 slope. If the slope is 0, then you don't have to apply any external force for this body to remain at rest. No external force is needed. The external force must be 0. And we obtain this immediately. If alpha is 0, then force is 0. Yes, that's reasonable. if alpha is, for example, if alpha is increased up to 90 degrees, if alpha is increased up to 90 degrees, so alpha is here and the body is here, and we need to exert such a force that the body is at rest. It's obvious from intuition that the larger is angle, the closer is this surface to the vertical, the larger should be the force. And finally, when alpha tends to 90 degrees, when this slope tends to vertical, then the force exerted here should tend to infinity. And that's quite obvious from this expression. If alpha is 90 degrees, then tangent alpha tends to infinity, and the force will be infinite. That's all physically reasonable. So analysis of this formula shows that it seems to be correct. We made no mistake. And also, if there is some coefficient, non-zero coefficient of friction, then what we notice from this formula, we notice that the larger the coefficient of friction, if it grows, if k grows, if k is increasing, then the numerator of this formula is decreasing, and the denominator is increasing. So if k is increasing, then this expression is decreasing. The larger the k, the smaller the F applied, the force applied to the body. That's also quite reasonable, because if the coefficient of friction is growing, then you don't need to support this body with large force. The force may be diminished down to zero if the coefficient of friction is large enough. So when coefficient of friction is growing, the force becomes smaller and smaller. That's quite reasonable. Everything is good in this formula. And also the dimension is good, because this is the dimension of force, which is measured in newtons, and this gives you no additional dimension, so units of measurement are correct. If you try to draw a graph of force necessary to support this body at rest as a function of alpha, then if some coefficient of friction is present, if some coefficient of friction is there, then you see that if coefficient of friction is 0, yes, we obtain the result. But if the coefficient of friction is negative, it can be negative. We also already discussed this possibility. The coefficient of friction may be equal to -1. If you substitute here -1, then we will obtain the formula for a negative coefficient of friction. Negative means that the force of friction in our notations is directed downward. We discussed it. And so if it's directed downward and coefficient of friction is -k, then it's obvious that the force will be maximum possible force. Maximum. So the maximum force, the maximum value of the external force applied to the body will be obtained from this expression if k equals -1. So that will be mg sine alpha plus cosine alpha divided by cosine alpha minus sine alpha. That is for largest possible forces. If you increase the force larger than this magnitude, then the value of this expression, then the body will start sliding upward. We don't need it. So this is largest possible force. And the minimum possible force, which is required to sustain, to keep the body on the surface at rest, the minimum force is also easily found from this expression. If k becomes larger, if it grows, then the numerator of this formula becomes smaller, and denominator will become larger. That means that if k becomes larger, then all this expression becomes smaller. And so the minimum possible force will be obtained from this expression if k is the largest, has the largest possible value that is +1. So the minimum possible force will be mg sine alpha minus cosine alpha and cosine plus sine. So at any given alpha, at this one, you will have maximum and minimum forces. And any value between these two quantities will be good. Any value of force will satisfy the conditions of the problem that if any force between these two maximum and minimum values is acting on the body, then the body remains at rest. This is the condition of the problem. So any force between maximum and minimum will be good. If you try to draw a picture of this, if you try to draw a curve, a graph of this function as f as a function of alpha, for example, for maximum force, so what will this look like? Look here, if alpha tends to 45 degrees, cosine of 45 degrees has the same value as sine of 45 degrees. So if alpha is 45 degrees, then the denominator of this formula tends to 0. And if you divide by 0, you get infinite value of the maximum possible force. What is infinite value for 45 degrees? That is 45 degrees. And at this point, the force will be infinite. But if alpha is 0, if alpha is 0, then sine is 0, but cosine is equals to 1. So if alpha is 0, then the force equals mg. That will be mg here, and the force for 0 angle, the force will be equal to this quantity. And if alpha tends to 45, then the maximum force will go to infinity. So this is maximum value of the force. And so you can also draw a graph depicting the minimum value. The minimum will start from minus mg, and it will go something like that. And also if alpha tends to 90 degrees, then if alpha is 90 degrees, then sine equals to 1, and this is 0. So the total force, the minimum force will be mg. The minimum force for 90 degrees sine alpha. The minimum force will be mg. And so the any point inside this figure, any point will give you a force which is quite reasonable, which will satisfy the conditions of the problem. Any force from this area applied to the body will ensure that the body is at rest. It's in stable equilibrium. So these forces are positive forces in our convention are directed here. So positive forces press the body against the surface, and these forces are negative. And we, according to our convention, negative force is when we pull the body by a string and try to pull the body so that the body remains at rest here. So it's impossible to keep the body at rest if you pull the body and the angle is larger than 45 degrees. That's reasonable. 45 degrees is the maximum possible angle when the body is at rest by itself without any external forces, only due to force of friction. So the whole picture is like this. Just a few students understood all this phenomena and gave me the correct formula. Just a few students, and none of you gave me this graph to depict the behavior of the forces. So I repeat, any point inside this area will satisfy the condition of the problem. That is, any point, any force corresponding to any force corresponding to certain angle here, any point in this area, that is any force corresponding to the angle shown along the horizontal axis here, any force, any point here corresponds to possible force, which satisfies the condition of the problem, satisfies the requirement that the force is acting horizontally on the body and the body remains at rest. That's it. That's the solution of the second problem. The very good solution when you give me this range between maximum and minimum forces. But what I expected also is this graph, which should be given in order to present graphically what happens with the force at different, what are possible forces at different angles. That's very useful. This problem was probably the most difficult and the most complicated among all other problems of the written test. Now problem number 3, which is very simple. Most of students obtained correct answers. Problem number 3. A body moves at a speed of 4 meters per second. Well, like this. 4 meters per second. And it catches up with the similar body moving along the same line at a speed of 2 meters per second. So at the same line, similar body moves at a speed just half the speed of the first body, just 2 meters per second. Certainly, sometimes there will be some moment in time when the first body will collide with the second body. Determine the speeds of the bodies after an absolutely elastic central impact, after an absolutely elastic collision. Well, most of students were absolutely correct when they applied the law of conservation of momentum and the law of conservation of energy, which is applicable here because the impact is absolutely elastic. But the simplest way to solve this problem, the simplest method, is to go to the center of mass reference frame. So this is the center of mass of the two equal bodies, similar with the same mass. The center of mass is just in the middle between these two bodies. And if we go to this system of reference, yes, we certainly understand that this center of mass moves at the velocity, which is the mean velocity between these two velocities. So the velocity of the center of mass is the mean, it's just 3 meters per second. The average, the mean between, arithmetic average between 4 and 2. And if we move to this center of mass reference frame, then with respect to this reference frame, the first body will have the velocity just 1 meter per second. And the second body will have opposite velocity, also 1 meter per second. And so in the reference frame associated with the center of mass, the center of mass frame, the two bodies move at the same velocity and collide, and the collision is absolutely elastic. So after collision, they will move in opposite directions with the same velocities because the masses are the same. Masses are the same, and in the reference frame of the system of the center of mass, two balls move, collide, and then they move in opposite directions with the same velocities. After collision, the velocities will be the same in the center of mass reference frame. So that will be minus 1 meter per second, and that will be plus 1. That was minus, and that will be plus 1 meter per second. And now we move backward from the center of mass reference frame to our laboratory reference frame. And certainly we understand that we must somehow combine these two velocities. 3 meters per second minus 1 will be 2 meters per second for the first body, and 3 meters per second plus 1 will be 4 meters per second for the second body. So that's the final answer, which is most easily obtained. The final answer is most easily obtained if you go to the center of mass reference frame first, and then go backward to the laboratory reference frame. Then all the solution is just primitive arithmetics without the necessity to solve system of equations related to the law of conservation of momentum and conservation of energy. Yes, that's correct. If you apply the laws of conservation of energy and momentum, that's correct. And the final solution will be the same. But the easiest way to obtain the solution is to go first to another reference frame, another reference system, and then backward, and then jump backward. So that's the simplest way to solve problem number 3. Problem number 4. Problem number 4. A stone is thrown at a speed at initial speed of 20 meters per second at an angle of 60 degrees to the horizon. So the stone is thrown so that the degree is alpha is 60 degrees. Yes, it's 60 degrees to the horizon. 60. In what time? So we need to find. Может... Они могут включить еще и дальше крутить все это. Я боюсь, что они начнут сейчас это повторять и повторять. Нет, а это что, здесь у нас динамики в этой аудитории, да? Ну, давайте продолжим. Okay, so we continue. That was a fire alarm announcement, which we believe is false. As it most often the case, the fire alarms are false. So, anyway, the stone is thrown at 60 degrees, and we need to find the time interval which is necessary for the velocity to turn, for the vector of velocity to turn from its initial direction. The vector of velocity turns by some angle beta, which is 15 degrees. So we need to find the time interval when the vector of velocity will turn by 15 degrees. So when a stone is thrown at an angle to the horizon, we may have two components of the velocity vector. The horizontal component, Vx, is the initial velocity V0 cosine alpha, and the vertical component, Vy, is the initial velocity sine alpha. So the horizontal component remains constant. It doesn't change in time because no forces are acting in horizontal direction. We neglect the forces of air drag, the forces of air resistance. But the vertical component will not be constant. The vertical component as a function of time will be the initial vertical component, which is V0 sine alpha, minus acceleration of free fall times t. Acceleration of free fall is directed downward so that it tends to diminish the vertical velocity as the stone is flying along its trajectory. So when the final degree at some moment of time will be less by 15 degrees, what does it mean? It means that the initial degree minus this beta will be 60 minus 15 will be 45 degrees. So at this particular point, the velocity is directed at 45 degrees to the horizon. It means that the vertical and horizontal components of this velocity will be the same. The vertical and horizontal components will be the same. This lag equals to this lag. If they are the same, then we have a very simple equation, which means the initial velocity along the horizontal direction, that one, which is constant in time, must be the same as the vertical component at some moment of time. That will be sine alpha minus g. Well, put it delta t, as I need to find this time interval delta t. So from this equation we must find delta t, and immediately we obtain v0 sine alpha minus cosine alpha over g. And that will give us v0 is 20, g is approximately 10, and that will sine alpha, sine of 60 degrees, will be square root of 3 over 2 minus cosine alpha. Cosine of 60 degrees is 1 over 2. So what we obtain here, 20 divided by 10 gives us 2, and 2, if we put it inside the round brackets, will give us square root of 3 minus 1, which is approximately square root of 3 is approximately 1.7, minus 1 is 0.7 what? Seconds. 0.7 seconds. So just in 0.7 seconds, the vector of velocity will turn by 15 degrees. That's the final answer to this problem. In 0.7 seconds, less than 1 second. In less than 1 second, the vector of velocity of this stone will turn by an angle 50 degrees. And from the original 60 degrees, it will fly in the direction of 45 degrees to the horizon in just less than a second. And the last problem, number 5. A uniform solid disk, of some radius rolls smoothly on the floor, with some initial velocity. So it's rotating and rolling with some velocity, then up a ramp inclined at an angle of 15 degrees to the horizon. Then there is a ramp, a slope or inclined plane, whatever you call it, at the angle 15 degrees to the horizon, and the disk goes up the slope up to the maximum point, and we know that it's given that the disk passed 2 meters along the ramp before stopping. So this distance is 2 meters. This distance L along the ramp is 2 meters. So the disk goes up and stops at this point, and what else? Then it will go down and roll backward. But we are not interested in this further developments. We need just to calculate what was the initial speed. What was the initial speed of the disk? If we know that it went up the ramp, just along the ramp by 2 meters, so that the height to which the disk went can be calculated as, because h divided by L is sine alpha, so h will be L sine of 15 degrees. So the disk went to this height. All the students understood that we have to apply a law of conservation of mechanical energy, which is the original initial energy, which is kinetic energy, must be equal to the final energy, which is potential energy of the disk. But not every student understood that we must take into account both the energy of the motion of the center of mass of this disk and the rotational energy of this disk, because it's rolls, so it's rotating at some angular velocity v. So if the radius of the disk is r, then the angular velocity is the linear velocity of its center of the center of disk divided by r. That is a simple kinematical expression which we studied during the first 2 lectures of this course. So the initial kinetic energy in this particular problem must be equal to the final potential energy. The kinetic energy equals to the energy of motion of the center of mass plus the energy of rotation, I omega squared over 2, where I is the moment of inertia of this disk. Moment of inertia. For the uniform disk, what does it mean uniform? It means that the mass is distributed uniformly through the disk. For such a body, moment of inertia is mr squared, the mass of the disk, radius squared over 2. And this should be equal to the final potential energy. Everybody understood it was mgh. It says in the problem that the disk radius is much smaller than 1 meter. What does it give you? Why is such a condition? The disk radius is much smaller than 1 meter. And this distance is 2 meters. So the disk radius, if it was large, the disk radius, if it was large, then the height of the disk would be calculated in somewhat more complicated fashion than this formula gives you. This is the simplest formula, which gives you the height of the center of mass. The center of mass moves to this height with respect to its original position. But if the radius is large, we will have to take into account that the center of mass is not above this point, but somewhat displaced to the left, because the disk rolls up the slope. So in order not to complicate the problem with these calculations, geometrical calculations of the real height of the center of mass, in order to make the problem more primitive, we have assumed that the disk radius is much smaller than this length and much smaller than this length, so we don't have to take into account these geometrical complications. So the simple formula will be this one for calculating for calculations, and if we take into account that the moment of inertia is mr squared over 2, and we substitute omega here, which will be v squared over r squared, and also divided by 2. And then we obtain for this term in the formula r squared cancels, and we obtain mv squared over 4. And also in this equation, mass will cancel. Mass is here, and mass is here. It will cancel. And what we obtain finally will be v squared over 2 plus v squared over 4 equal to gh, and h is L sine alpha, sine of 15 degrees. So this gives us v squared multiplied by 3/4, which is GL sine alpha. So v, the velocity which we need to find, the original initial velocity of the disk center, will be from this equation will be 2 square root of L g sine 15/3. That's the final answer, and what remains to be done is just to substitute numerical values for L, which is 2 meters, and G, which can be taken as 10. And you may easily use your calculator to assess what is sine 15 degrees. And if you carry out all these calculations, you will find that the initial velocity of the disk is about, I have forgotten the value, is about 268 meters per second. If you carry out all the calculations correctly, L is 2 meters, G is 10 meters per second squared. So 2 times 10 divided by 3, and sine of 15 degrees is easily found using a calculator. If you take the square root and carry out all these calculations, you will find that the original velocity of this disk, the initial velocity, was just a little bit less than 3 meters per second. So what was the mistake of many students? They did not take into account this term, which reflects the rotational energy. Rotational energy. The total energy cannot be reduced only to the kinetic energy of the moving body. If the motion is translational, that is, the body moves remaining parallel to itself, then the kinetic energy will be calculated by this formula. But if the body not merely moves, if not only the center of mass is moving, but the body is rotating, then some rotational kinetic energy must be taken into account. Many students have forgotten about this law of physics for kinetic energy. So that is the solution of problem number 5. Now, after discussing all the problems of written test, we must go to a next topic. The next topic will be some properties of liquids. Some properties of liquids. We have recently discussed properties of gases and properties of ideal gases and the equation of ideal gas. And the first law of thermodynamics, which is just a law of conservation of energy as applied to systems consisting of many atoms and molecules. So after discussing the properties of gases, we go to the properties of liquids. I told you that a liquid, well, you understand, everyone knows what a liquid is. A liquid body is has very peculiar properties, which differ much from the properties of gases and differ from the properties of solid bodies. And the reason behind these different properties behind this behavior is that the energy of interaction between molecules in a liquid is of the same order of magnitude as the energy of kinetic energy of motion of molecules. So if the kinetic energy is increased, the temperature of the body is increased, then the molecules will go away from each other and the liquid will evaporate, and we will have a vapor instead of liquid. We will have gas. But if the temperature is not very high, the molecules will stick together and form a liquid when the energy of kinetic energy of motion is approximately of the same order of magnitude, approximately equal to the bond energy, the energy of interaction between molecules. But if the energy of interaction becomes, if the kinetic energy is much smaller than the energy of interaction, then liquid turns to solid state. The liquid is frozen. The water turns to ice. That is when temperature is decreasing and the kinetic energy of the motion of molecules becomes smaller and becomes less than the energy of interaction between molecules. So that is the general picture of liquids and gases. And what is liquid has some very peculiar properties, and we will consider these properties shortly because we don't have much time. First property of liquid. First, the surface of liquid at rest in the state of static equilibrium. The surface of liquid is always horizontal. The surface is horizontal. It's better to say that the surface is perpendicular to the vector of acceleration of free fall. That is always the case, whatever liquid you observe. The liquid in the sea, in the ocean, in a bottle of water, anywhere, the surface of liquid turns out to be perpendicular to the vertical. And it's easy to understand why this is so, because if the surface was not perpendicular, then any small portion of liquid will tend to slide down this slope. If the surface of liquid was not horizontal, if it formed some angle to the horizon, then that would be a sort of inclined surface for any small droplet of liquid here, and any small droplet would flow downward from this surface. And that flowing means that no static equilibrium is possible. If the surface of liquid is somewhat inclined at some angle to the horizon, then this cannot be a static equilibrium state. If we consider the state of static equilibrium, when liquid does not move, when it remains at rest, every small volume of liquid remains at rest, then necessarily the surface of liquid is horizontal. Otherwise, it would flow down the slope, and there would be no equilibrium, no static equilibrium of liquid. So liquid at rest always has its surface horizontal or perpendicular to the acceleration of free fall. If we consider the Earth, the major part of the Earth's surface is formed by oceans, so we may consider the Earth as consisting of liquid. Actually, the Earth has a hard core inside it, and then this is hard core, and all the other volume, all the remaining volume is liquid and contained of melted stones, which is called magma. All the Earth is liquid, and only a very thin crust on the surface of the planet, very thin which is just a few dozens of kilometers, from 10, we'll say, to 19 kilometers. That is very small distance as compared to the Earth's diameter, or to the Earth's radius, which you know is 6,000 kilometers. And very, very, very thin solid crust on the surface forms the ground and the soil on which we live. And all the planet inside is liquid, actually. So the laws of liquid can be applied to the planet. At first approximation, if the planet is at rest, if it's not rotating, then all the vectors of free fall acceleration will be directed to the center of the planet, everywhere to the center. And therefore, the planet figure will coincide with the sphere. At first approximation, the planet is the sphere because it's liquid inside. And even the planets which are not liquid inside, which have solidified, they were liquid some billions of years ago, so they had plenty of time to form a spherical shape, and then they solidified, and then they became all solid. But the shape remained. The shape of the planet remains spherical, even for those planets which are solid. But the Earth is not solid. The Earth is, our planet Earth is liquid. So at first approximation, its form is spherical. That is only the first approximation. If we take into account the rotation of the planet, rotation about the axis which goes through the North Pole and South Pole, and the Earth is rotating, so that in this direction the Earth is rotating. If you take into account rotation, then it's clear that the planet itself, rotating planet, is not an inertial reference system. It's not an inertial frame. So it's non-inertial, and therefore there are forces of centripetal. There is some centripetal acceleration, and actual acceleration of free fall will not be directed to the center of the planet. Actual acceleration will be directed somewhat at an angle, and therefore the ocean surface or the planet surface will not be perpendicular to the radius of the planet, but it will be perpendicular to another direction. And as a consequence, the planet turns out to be somewhat compressed from the poles, and the shape of the planet, or the figure of the planet, looks more like a ellipsoid of rotation, or ellipsoid of revolution. So the ellipsoid of rotation is the actual form of the planet because of its rotation, because of centripetal forces. And the planet actually is flattened at the poles. It's flattened at the poles, and it's bulging at the equator. So this is the equator, and the planet is bulging out at the equator. But this non-spherical form of the planet is looks like a sphere, because this is a very small. This is a very small distance. The flattening at the poles is about 10 kilometers, and also the bulging at the equator is also about 10 kilometers. And 10 kilometers, about something like this. And 10 kilometers is very small as compared to the radius of the planet. So the planet may be well approximated by a sphere, but only if you need a more precise measurement of coordinates on the surface of the planet. Then you will take into account that the planet is an ellipsoid of revolution, some ellipsoid which differs from a spherical surface. But this is very small. This is very small as compared to the radius. So the actual figure of the planet is very close to a sphere. So that was the first property of the liquid. And the second property will be the pressure inside the liquid. Imagine a vessel and the liquid inside, and the liquid has height h, and the vessel, cylindrical vessel of the cross-section S. The area of its bottom is S, and so there is a liquid, and if the liquid density is rho, the density is measured in kilograms per meter cubic. That is, the density is the mass of a body contained in a unit volume. The mass measured in kilograms and unit volume, meter to the power of 3. So if there is some liquid here of the known density, then we can easily calculate the mass of this liquid. The mass of the liquid will be its density times volume occupied by the liquid. And in our particular case, volume is hs. And if we multiply by g, by the acceleration of free fall, this equation, then we obtain rho g hs. And this is the weight of the liquid. This is the force with which the liquid is acting on the bottom of this vessel. The force, that is the weight of the liquid, mg. And we know that the pressure is defined as the force acting on a unit area. So if we take this expression, take this equation, and divide it by S, we will find pressure, which is force divided by S, and pressure from this equation will be equal to rho gh. So this is the pressure of liquid at the depth h, whatever h you take. I have taken h equal to the whole depth of this liquid, but I could have taken h as something like this. And at this point, at the depth h, the pressure of liquid will be calculated by this formula. That is the force acting inside the liquid on the unit area, whatever area you choose. And the third property of liquid will be the property which says that the pressure, forces of pressure inside the liquid are transmitted in liquid in all directions. So if we have pressure here, I will draw again. If we have some pressure at this point, and we choose we imagine some small volume of liquid, and there is a force of pressure acting on it, we must understand that forces of pressure act in all possible directions. In all directions. Why? Because this small volume of liquid is at rest. Why is it at rest? Because we consider the liquid which is at rest, the liquid in static equilibrium. We consider this simple case. And in this simple case, every small volume of liquid is at rest. And therefore, all forces acting on it from different directions cancel each other. And therefore, if there is a force acting in this direction, there is a similar force equal and oppositely directed. So all forces of pressure act in all possible directions inside the liquid because the liquid is at rest. If there is some motion inside the liquid, if there are some water flows inside it, then this will not be the case. Then pressures acting on any volume will be different from different sides. And this difference in forces will cause this small volume of liquid to accelerate and move according to some complicated trajectory inside the liquid. If the liquid is in motion, then the pressure is not equal in all directions. But if the liquid is at rest, and this case we only consider now, if the liquid is at rest, then pressure is distributed equally along all the directions. So this pressure is not directed downward only, it's directed everywhere. If you take a small if you take just a small device to measure pressure, and you measure pressure on this surface, and no matter how you turn the device, no matter what is the direction of this surface, it may be directed so, or it may be directed in this way, or it may be directed in this way. Any surface will feel the same pressure, regardless of its direction. So the pressure can easily be calculated. It depends on the density of water, acceleration of free fall, and the depth in water, depth in a liquid. And we must understand that this pressure is not a vector. This is a scalar pressure because it's acting in any direction, whatever you choose. In any direction, the pressure is the same. Now, property number 4. If you take some vessel with liquid and you put inside the liquid an arbitrary body, so this is liquid and this is some solid body, whatever you put inside, then there is an Archimedes law. Archimedes law saying that there is some force acting on this body from the forces of pressure of liquid. There is some resulting force acting on the body. And this resulting force is called buoyancy force. A force of buoyancy, buoyance force. That means that the force is trying to lift the body upward. It's always there because there are forces of pressure acting on the surface of this body from different sides. There are forces of pressure. And we know that pressure depends on the depth. So forces of pressure here at the upper end of this body are smaller than the forces of pressure here. Here forces are larger. And therefore, the total force acting on this body will have a resultant, or the net force will be directed upward. Why do we know it, and how can we calculate this force? The Archimedes law says that if the volume of this body is V, that is not the volume of the whole liquid, but the volume of this body, then the force acting on the body equals the weight of the liquid in the volume of this body. There is no liquid in the volume, but imagine that we have taken this body away. Imagine that there is no body in this liquid. But we can imagine the same volume which was occupied by this body. The same volume is now occupied by liquid, and liquid is at a state of stable equilibrium. And it means that this liquid here, now it's not a body, not a solid body, but liquid, which is in the state of stable equilibrium, in static condition. This volume does not move. It's in static equilibrium. It's at rest. It means that the force of the weight of this volume of liquid is somehow balanced by another force, which is the force of buoyancy, which is the force of pressure from all surrounding liquid. So all the forces of pressure must be equal to the weight of the liquid contained in this volume. And the weight of the liquid is just the mass of the liquid times acceleration of free fall. And the mass of the liquid is exactly the density of liquid times the volume, this volume of this imaginary imaginary part of liquid, times acceleration of free fall. So as in static equilibrium, again, we consider only the liquid at rest. And if we consider the liquid at rest at this particular situation, in the situation of static equilibrium, this imaginary volume of liquid is at rest. It means that its weight, mg, is balanced by some forces of pressure from the outside liquid. And the forces of pressure can easily be now calculated, because we know that all this force of buoyancy is balancing the weight of the liquid, and the weight of the liquid can easily be calculated. So we know that whatever solid body we put inside the liquid, there will be a buoyancy force acting on this body by the surrounding liquid, and it can easily be calculated if we know the density of liquid and the volume of the body immersed into liquid. So that is the Archimedes law. What is the Archimedes law? A body submerged in a liquid experiences a buoyant force which is acting on this immersed body that is equal to the weight of the displaced liquid. And the buoyant force is directed vertically upwards and is applied at the center of gravity, of this volume of liquid. The center of gravity of the volume of liquid is the center of application, the point of application of the buoyant force. But the center of gravity of the liquid does not necessarily coincide with the center of gravity of this solid body. The solid body may have some non-uniform distribution of mass. It may have some mass here, a large heavy part here, and very, very light part with practically very small mass here. So the center of gravity of this solid body may differ from the point of application of all the forces of pressure, or the point of application of the Archimedes force. And therefore, if these points of application of two forces are different, then this body will tend to rotate. It will turn upside down, which sometimes happens if you immerse anything inside the water. The body may turn and float upwards. And so this turning and rotation inside the water is caused by the fact that the point of application of the Archimedes force does not coincide with the center of gravity of the body itself, of the solid body. These 2 points may be different in space, because that happens when the mass is distributed non-uniformly inside the solid body immersed in liquid. And the liquid itself has a uniform distribution of mass. So when you have a uniform distribution of mass in liquid and non-uniform distribution of mass in solid body, the center of gravity will be different. That's the reason behind this phenomenon. So we started to consider properties of liquids, and we will continue this discussion next time on Thursday. And now let me finish this lecture on this point.